The previous lecture, we have discussed a very simple case where a small element of some component was taken, where there was only one axis. There was stress on only one axis, right? And we calculated the normal stress and shear stress on an inclined plane. See, actually, in this, there are multiple cases, and this is the final case which we will study, which has everything that a stressed element can have. So, here we have this body subjected to direct stresses in two mutually perpendicular directions. So, you can see sigma x and sigma y in two mutually perpendicular directions. The normal stress has been applied. Along with the simple shear stress, you can see tau xy also, which is applied on this element, right? Now, whenever the shear stress is applied, usually there is a reaction of this because you need to keep the element in equilibrium. So there is a opposite reactive stresses, shear stress, which is active. So that is shown in this picture. And this is the wedge which is formed by this inclined plane, and the normal stress and the shear stress. Those are shown here. Now we will try to derive an equation for this. This will be the general equation which can be used for all the cases. Now let us say there is only normal stress in one axis and shear stress. So sigma y will become 0, or if the stress is in y direction and in x direction it is not there, then sigma x in this equation will become 0. And if shear stress is not there, then in the equation tau xy will become 0, right? So like this, this will be a general equation which you can use it. Okay, now let us try to derive the expression for this. Uh, Let sigma x be the tensile stress along the x-x axis, that is the major tensile stress I have considered, and sigma y is the tensile stress along y-y axis, and I call this as minor tensile stress. Now, for simplicity, I have kept both as tensile stress. We can change this to compressive also. In your numericals, you may get compressive stress. So we have discussed about the sign convention. Compressive stress is taken as negative and tensile stress is taken as positive. So in your equation, sigma, let us say sigma x is compressive, then it will become minus. If sigma y is compressive, then that will become minus. That's it. Right? Otherwise, there is no change in this expression. Tau xy is positive shear stress along the x-x axis. If you see here, this is making a clockwise rotation. This is like this is like this, right? Tau xy. So it is making a clockwise rotation. The element tends to rotate in clockwise direction. That is why we have taken it as positive. Now let us say if it is in anti-clockwise direction, reverse, then you just have to put this as minus in your equation. That's it. Theta is the angle of oblique plane AB with respect to BC. See, BC is the major tensile stress, right? Sigma x. BC is along sigma x, which is my major tensile stress. So, in all the derivation we have used here, this angle theta is with respect to major tensile stress. In I think R.K. Bansal, he has taken the plane like this, inclined plane like this, and the angle theta is completely different. So his equations are different. That doesn't mean that that is wrong, right? Because see, now if you take this angle as theta, then you get whatever equation we are going to get. Now, instead of this, if you take this angle as theta, Now for this angle, sin theta will be cos theta will be sin theta because it is other angle, right? So that is the only difference you are going to get. But actually, the answers that you are going to get will be same from both the equations. Now let us try to derive this. The wedge ABC, that is this, I have shown it separately here, is under equilibrium under these stresses. There is normal stress, major tensile stress sigma x, minor tensile stress sigma y, and shear stress tau xy and tau xy here, right? And in order to keep this in equilibrium, there is a normal stress which is perpendicular to AB and a shear stress along AB which is tau, which is tangential. So we have to find this normal stress and shear stress. The horizontal force on AC, this is my AC. I'm calling that as P1. P1 is equal to sigma x into AC. See, x is the sigma x is the horizontal stress there. So stress into area. I have considered a unit thickness element. So stress into area, and it is in this direction, left direction. Similarly, P2 is the vertical force on AC. See, vertical force is due to this shear stress, right, tau xy. This is in upward direction. So the load will be shear stress into the area. That is why we have tau xy into AC. Then vertical force on BC, that is this plane. Vertical force is sigma y, which is acting in downward direction. So sigma y into BC will be the load at that point, and the horizontal force on face BC, the horizontal stress is tau xy, that is shear stress. So tau xy into BC, and it is in this direction, right? Now we have all the loads. We will resolve this in the direction normal to this plane AB and along the plane AB, right? So resolving the forces in the direction normal to plane AB. So we get Pn now. So Pn is P1 sin theta minus P2 cos theta plus P3 sin theta minus P4 sin theta, plus and minus because they are in opposite direction. That is why we have these signs. Now, using this, I can calculate the stresses, right? So I have just substituted P1, P2, P3, P4 values as sigma x AC, tau xy AC, sigma y BC, and tau xy BC. Now, from this triangle, uh, okay, first let us resolve the forces along the plane, right? Tangential to the plane. So Pt is equal to P1 cos theta plus P2 sin theta minus P3 sin theta minus P4 cos theta. Right? Again substitute the value, so you get this equation. Now what we'll do is we'll try to find the normal stress. So I have the normal load on the inclined plane. So that normal load divided by AB will give me the normal stress sigma n. So Pn by AB is equal to sigma n. So this is Pn, which we got in the previous step, and divide this by AB. Now what is AB? From the triangle, AB is equal to AC is the hypotenuse. So if you take sine relation, sine theta is adjacent by opposite by hypotenuse. AB is the hypotenuse, AC is the opposite side. So AC by sine theta, and cos theta is adjacent by hypotenuse, and BC is the adjacent side, BC by cos theta. So why I have this is in this expression I have AC at some place and BC at some place, but I'm dividing by AB. So individually I will divide this by AC by sin theta or BC by cos theta, so that this AC and BC gets eliminated from this expression. Therefore, sigma n is equal to, here if you see AC sin theta, so I have divided by AC by sin theta. This is AC cos theta, so divide by AC sin theta, AC by sin theta. And here I have BC cos theta, so divide by BC cos theta, BC by cos theta. And here I have BC sin theta, so divided by BC cos theta. Now this sin theta and cos theta in the denominator will go to the numerator, and AC here and BC here gets cancelled, right? So what we get is, this becomes sigma x sin theta into sin theta. So it becomes sin square theta. This is tau xy cos theta into sin theta, right? Sigma y cos theta into cos theta, so it becomes cos square theta. Tau xy sin theta into cos theta, right? So this is the thing we get. Now we are using the identities of the trigonometry of half angles, right? So sin square theta is equal to 1 minus cos 2 theta by 2, and sin theta cos theta is equal to 1 plus cos 2 theta by 2, right? So we are using these, sorry, cos square theta is 1 plus cos 2 theta by 2. So using this and simplifying or grouping the common terms, we get sigma x by 2 into 1 minus cos 2 theta plus sigma y by 2 into 1 plus cos 2 theta minus sigma, sorry, tau xy sin theta cos theta, because there are two terms here, minus tau xy sin theta cos theta minus tau xy sin theta cos theta. So it becomes 2 times tau xy sin theta cos theta. Now expand this term, right? So what I get is, so sigma x by 2 minus sigma x by 2 cos 2 theta, same thing here, but this is plus, so it becomes like this. Now group the terms. So this is without any trigonometric function, so it becomes sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta, right? See, this is plus, here it is minus, so minus of minus, it will become plus. Then I have minus tau xy sin 2 theta. This is sin theta cos theta is equal to 2 sin 2 theta, right? We have that identity, so that 2 gets cancelled. So this is the equation for normal stress. Now the shear stress or the tangential stress on plane AB, tau is equal to tangential force by AB. So in the same lines, use the tangential force equation divided by AB. So tau is equal to sigma x. Again, here I have AC and here I have BC. So I am dividing this with AB in terms of AC and sin theta or BC and cos theta, right? And when you simplify, you get the expression like this. Now group the terms, expand the brackets and group the terms. The final expression we get is, tau is sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. Okay, so these are the two expressions for finding the normal stress and shear stress. Now if it is the normal stress in only one axis, one direction, then sigma y can be made as 0. If shear stress is not there, then you can make this as 0. So this will be a general equation. The principal planes, we have discussed this in the previous class. Principal planes are the one where the shear stress is not present, right? So we have the equation for shear stress. So if you equate that to 0, you will get the principal planes. So we have this shear stress is sigma x minus sigma y by 2 sine 2 theta minus 2 xy cos 2 theta equal to 0, or sigma this term which is negative goes on the other side. So we have sine 2 theta and cos 2 theta. So bring this cos theta on the other side, it becomes sine 2 theta by cos 2 theta, or tan 2 theta, which will be equal to 2 times tau xy divided by sigma x minus sigma y. Now, if you make this as a triangle, uh, so this is the 2 theta angle, right? And the numerator of the tan is the opposite side, and denominator is the adjacent side. So 2xy will be opposite side, and sigma x minus sigma y will be adjacent side. Now we have two conditions in which this equation can be satisfied. One is the opposite side is minus 2 tau xy, and adjacent side is minus of sigma x minus sigma y, and the other one is plus 2 tau xy, and the adjacent side is sigma x minus sigma y, right? So if you use these values, right, for tan 2 theta, then you get sorry, from this you get sine 2 theta and cos 2 theta, because in my expression for principal stresses I have sine 2 theta and cos 2 theta. So sine 2 theta from this, now this will be the hypotenuse square of sum of square of these two sides. So if I take this, I will get one principal stress. If I take this condition, I will get the second principal stress. So these two are giving me basically two principal planes, right? So the above condition can be fulfilled by two cases, which gives us the two principal planes which are mutually perpendicular to each other. So the first principal plane, or the condition, is sine 2 theta principal plane 1 P1 is minus 2 tau xy by root of this, and cos 2 theta is adjacent side by hypotenuse. And the second condition, that is this, will give me sine 2 theta on principal plane 2 as this, and this is cos 2 theta. If you see, this is only minus here and there is no minus here. That is the only difference, right? So now we have to put this value of sine 2 theta P1 and cos 2 theta P1 in normal stress. You will get first principal stress, and if you put sine 2 theta P2 and cos 2 theta P2 in the normal stress, you will get the second principal stress. Principal stress are the normal stress. Now we can calculate the principal stress as sigma P1 is equal to sigma x plus sigma y by 2. So this is my expression. Now put cos 2 theta and sin 2 theta, what we got in the previous slide. So when I substitute cos 2 theta and sin 2 theta, I get like this. Now see, sigma x, sigma y, here also I have sigma x, sigma y. This minus and minus will get plus, right? So it will become sigma x minus sigma y whole square, and here also it is minus tau xy into minus 2 tau xy. So when you multiply that, it will become plus 2 tau xy square, right? So, and further when you simplify, because the terms denominator of both the side are same, only the numerator is different. So when you take that common factor and cancel out, you get the final expression as the first principal stress as sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 whole square plus tau xy square, right? And if you put in this expression cos 2 theta and sin 2 theta of second principal plane, we will get this. This is the second principal stress. If you see, everything is same, only here I have plus, here I have minus, and tau max, that is the maximum shear stress, it will be same for both the planes, right? Because you get a whole square inside the root. So tau max is sigma x minus sigma y by 2 whole square plus tau xy square. So if you observe this, see, this is the normal stress part, and only inside the root here I have the shear stress, right? Same is the case here. This is the normal stress, and this is the uh, shear stress part. So basically I can say this will give me the normal stress and this will give me the shear stress, right? Now if shear stress is not present, if this is 0, then it will be only normal stress here, right? Or if normal stress is not there, then it will be only shear stress, right? So like this we can calculate. These are the final equation. So you have to remember basically one equation. Principal stress is sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 whole square plus tau xy square. And second one will be, you put minus instead of plus here, and maximum shear stress is only the term in this square, right? So like this we can calculate. Is there any question?